Good evening. So today we are going to have our final lecture on bucklings. And I realized that I have not posted homework number 2. I'll post homework number 2 tomorrow. And do not worry, I will give you adequate time to complete homework number 2. So after buckling, I hope to start a new topic, which is known as symmetrical centric bending. But first of all, a student point out to me that I've made a mistake in one of the equation, and indeed the student was right. So this is a correction on week 3, Tuesday, page 1. And over here we have a relationship for eccentric buckling, where we have stress max is equal to P over A bracket and then the rest of the term. The mistake I make is over here. Okay, the mistake I make is over here. So the next line, okay, the next line should not look like this, but rather secant 1 over 2. Okay, not secant over 2. So this term over here, if I were to tidy things up better, it should be secant and then bracket this term over here. Okay, then from here to continue, you have P over A bracket 1 plus by EC over R squared secant. And I still remember we took out half, and then we have L over R, and then the whole thing square root P over EA. Okay. So that is the final form. So again, I like to highlight this is correction for week 1, page 1. Okay. Right. So that part is sorted out. So what we're going to do is now we're going to finish off buckling. So we are going to design. Before I go on, any questions so far? Are we okay? All right. So
Is the Y max formula still the same?
yeah. I
Okay.
mean, what I did not write properly is before that I wrote it in terms. If you look at on Tuesday, right? This is where the discrepancy is. It's not secant over 2. It's secant half.
Okay. Okay.
Okay, so this is the correction part. So you look at the corrected part.
Yeah.
Okay, it's still stress max we're calculating, nothing changed. So the next one, we're going to finish off our final stage of buckling. So we're going to design structure steel columns other. Now we go back to centric loading. Okay, again. Okay, so based on laudable stress. So I'm going to recap. So what we have over here is design of structural steel. Okay, if the L over R is or if you look at between point A and point B, right? The empirical equation is stated in equation number 1, where the stress critical, which is on the y-axis, and the L over R on the x-axis is equal to 0.658 power of square root U over square root E, and then the whole thing bracket multiplied by the U stress. Okay. So as I mentioned, as we have written before, this is only valid when L over R is less than 4.71 square root E divided by stress U. Okay. Now, stress E, this is the function for stress E, or this is the equation for stress E, right? Now, the next one is between B to C. So now we are looking in between B to C now, between this range. We have to adopt equation number 2, where stress critical is equal to 0.7 stress E. So equation number 2 is only valid when the L over R ratio is greater than 4.71 square root of E over stress uses at this region over here. Then at point B, right, at point B means exactly at this point over here, we have this relationship that L over R is equal to 4.71 stress E over stress, Young's modulus over stress U. Now, I wrote this equation down where stress allowable. Now we are in the next equation over here. Yeah, I wrote this equation down. Is stress allowable is equal to critical stress divided by 1.67. So for this case, this is the sort of like safety of factor for structure steel during buckling analysis. Okay, just to clarify things up. So the factor of safety is equal to 1.67, right? And then this is equal to stress critical divided by stress allowable. Okay, so it's a sort of safety of factor that is commonly used when we design or when we design structure with structure, or we design buildings, okay, with structural steel. Okay, so as I mentioned in our last lecture, equation 1 to 3 are only valid for structural steel. Okay, if you change your material to become aluminum or wood, you cannot use this set of equation. Okay, you have to use another different set of equation, which you can find from our textbook. But due to time constraint over here, the process is the same. Okay, it's only the formulas are different. I am going to focus on structural steel. Any question from anyone so far? Okay, so I hope you understand. All right, so last week we started this problem. Okay, not last week, on Tuesday we started this problem, and I'm going to still do it again. Okay, so we can see a central load P must be supported by the steel bar AB, okay, using allowable stress design. So this question over here asks us to use the allowable stress design. So the allowable stress design, what it means over here, when they say we have to use allowable stress over here, is we have to use equation 1, 2, 3, and 4. Okay, so that is what we mean by allowable stress design. Again, in the exam or test, I will provide you with these equations. So they told us to determine the smallest diameter D of the cross section that can be used when P is equal to 24 kilopound force. Now, I'm only going to do A, okay, because B, the procedure of calculation is exactly the same. So we know that P will be equal to 25 times 10 to the power 3 pounds. Okay, and then we were asked, or we are given that the stress yield is equal to 36 times 10 to the power 3 psi. And we know, given to us, the Young's modulus is equal to 29 times 10 to the power 6 psi. Okay. So as you can see over here, at point A, it's just a pin over there. So when the fixture is a pin, moment is equal to what? 0. At the other end is also a pin, moment will also be equal to 0. So we have a conflict. So when moment is equal to 0, then we know that on the top is pinned, on the bottom it is pinned. So now we are going to find the equation. So pin on both ends. Okay, so we have pin on both ends. The L equivalent is equals to, so we go back to Tuesday's lecture, pin on both ends As you can see this diagram over here, pin on both ends. Right, so pin on both ends. As you can see, LE is equal to L. LE is equal to L. So this will be, so our length is 5.2. That is in feet. We have to change it inches. Now, the reason why we cannot work in feet, we have to change into inches, is purely because our stresses is in what? Pounds per square inch. Our stresses is not pounds per square feet. Okay. So 5.2 times 12, so it's 62.4 inches. So the next thing we are going to find is we're going to find the L over R ratio. Okay, we are going to determine the L over R ratio based on material properties, or based on Young's modulus and stress U. Okay, so if we go back to our notes over here, right, to find L over R, the function of L over R, right, is equal to 4.71 E over stress Y. Okay, so this will be equal to L over R is equal to 4.71, okay, square root of E divided by stress U. Okay, so this is equal to 4.71 square root. So we are given Young's modulus is 29 times 10 to the power 6 divided by 36 times 10 to the power 3. So this is equal to 4.71, or square root bracket 29 power 6 divided by 36 power 3, close bracket, multiplied by 4.71 is 13.68. Oh, no, 133, not 13, 133.68. Let me copy that figure. Okay, let me copy this figure to tell you what are we trying to do. So we have determined that the L over R ratio over here, right? We have determined the L over R ratio over here is equal to 133.68. Okay. So at this present moment, we don't know whether our structure is in the regime or in the region of operation from A to B, okay, or can we design our structure based on B to C? Okay. So the boundary, whether it's from A to B or B to C, is dependent on L over R is equal to 4.71 square root Young's modulus divided by stress U. So we have determined that value, and that value now sits at 133.68. Okay, now this structure over here, okay, by looking back this question, this structure over here can buckle in two plates. Okay, can buckle in two plates. So if I'm going to call this, I could not remember the last time. I'm going to look at it. Did I call which is X, which is Y? Wait, let me follow the same so you'll not be confused. Okay, X, Y, and Z. I'm going to use the same notation over here. So this will be our X. Then this will be our Y. And this will be our Z. Okay. So we have to now determine Here we have to determine on which plane